This question is about the reactions of organic compounds containing carbon, hydrogen, and oxygen. So that's helpful to begin with, and we know that the compounds that we're looking at shouldn't have any other atoms. But we're told that a chemist investigates two reactions of alcohol A, shown below. So we've got this alcohol here, and part one is asking us, what is the systematic name of alcohol A? So first of all, we already have the compound drawn, so we don't need to draw it for ourselves. But the first thing we should do is to number our chain, find our longest chain. So if we start here, we're going to number 1, 2, 3, 4. So our longest chain is 4 carbons long, which means that this is going to be butan 2-ol. We also have this methyl group here on carbon 3, so the systematic name of this alcohol is going to be 3-methyl butan 2-ol. Part 2 asks us, what is the structural formula of alcohol A? So first of all, we've got these two matching methyl groups here. So they're both CH3. And when we have two identical groups that are sort of indistinguishable, we put them in brackets and put a number next to them. So 2 of them. Then we have CH. Then we have CHOH. And finally, CH3. We're told that the chemist heats alcohol A, which I've drawn here, with an acid catalyst to form a mixture containing 2 alkenes. So we know that this is forming an alkene, and the reaction that uses an alcohol as the reagent and produces an alkene as the product is an elimination reaction, where we take the alcohol and one of the neighboring hydrogens, we lose water and gain a double bond. And the trick here is that either of the adjacent hydrogens can be lost to form the double bond. So one double bond is going to form here, and the other double bond is going to form here. So our two products, they're both going to have that 4 carbon chain that we started with, and the methyl group, but one is going to have the alkene here, the carbon-carbon double bond there, and one is going to have it here. And neither of them have the alcohol group. In this question, you'll get 1 mark for each of the structures. We're told here that the chemist heats alcohol A with sodium chloride and sulfuric acid. We need to construct a balanced equation for this reaction, and we need to show structures for the organic compounds in the equation. So we know that we're heating alcohol A with sodium chloride and sulfuric acid. So what is this going to do? Well, our sulfuric acid is going to donate a proton to the alcohol, which will turn it into water, which is then going to leave the molecule with a positive charge, and the chloride anion will replace the alcohol group, and we'll be left with a haloalkane. So our products are going to be like this. So in this question, you will get 1 mark for the correct product here, or correct products, and then the second mark will be for making sure that everything's balanced. Is everything balanced? Well, we've got the same number of carbons on both sides here. We've got 1 chlorine on each side, we've got 1 sodium on each side, and we also need our water here. So we'll form both a haloalkane. Since our sulfuric acid donated 1 proton to our alcohol group, it's going to be HSO4 minus, and that's going to form a salt with our remaining sodium, forming sodium hydrogen sulfate. And we're also going to form water from the donation of that proton from the acid to the alcohol group in our alcohol A. Compound B, shown below, is refluxed with excess acidified potassium dichromate 6 to form a single organic product. In this question, we need to complete the equation for this reaction. First things first, we need to think about exactly what acidified potassium dichromate is. And this is a bookwork section of this question, and we need to know that this is an oxidizing agent. It takes things like alcohols and turns them into ketones or aldehydes or carboxylic acids. So we need to look at compound B and figure out what functional groups we have. So we've got 3 alcohols present in this molecule, and I'm just going to circle those. And we need to think about what these are going to be oxidized into. So this OH here, it's bonded to a carbon, which is bonded to just one other carbon, making this a primary alcohol. And when we oxidize primary alcohols fully under reflux with excess oxidizing agent, it's going to become a carboxylic acid. Our second alcohol here is bonded to a carbon, which is bonded to 2 carbons, making it a secondary alcohol. And secondary alcohols can only be oxidized as far as ketones. Our third alcohol here is bonded to a carbon, which is bonded to 3 carbons, making it tertiary and meaning that it can't be oxidized by acidified potassium dichromate. However, now that we've thought about the classifications of our alcohols, we can start thinking about drawing our product. So we've still got this 4-carbon chain as our backbone. We've still got this methyl group here on our second carbon. This alcohol was tertiary, so won't be oxidized under these conditions. So this is still present. This carbon here was a secondary alcohol. When this is oxidized, it also abstracts the proton from the carbon, forming a ketone. So we're going to have a carbonyl here. And finally, this carbon is going to be oxidized into, this alcohol is going to be oxidized into a carboxylic acid. So we can add that in here. Now we know that when we do oxidations with acidified potassium dichromate, we form water as a byproduct. So we need to think about how many steps of oxidation we've gone through to balance our oxidizing agent. And we did 2 steps of oxidation with the primary alcohol and 1 step of oxidation with the secondary alcohol. So this is going to be 3 equivalents of acidified potassium dichromate, which has been drawn with this O in square brackets to symbolize an oxidizing agent. And now we've done 2 steps of oxidation from alcohol to carbonyl, which are the ones that produce water. So we need 2 molecules of water, and now this is all balanced. So the 2 marks available here, the first one is for the correct organic product, and the second mark is for the fully balanced equation. The flowchart below shows some reactions of compound C. In the boxes, draw the organic products of these reactions. So first of all, we've got compound C here, which is an alkene with 2 carboxylic acids coming off of the sides, and it's symmetrical as well. So we have 3 sets of conditions. We've got excess methanol and sulfuric acid. We've got steam with phosphoric acid, and we have polymerization. So first of all, we've got these conditions here. We've got the excess methanol sulfuric acid, and these are esterification conditions. These are hydration conditions here, the steam and phosphoric acid catalyst. Hydration of an alkene is when we turn it into an alcohol. And polymerization is going to be an addition polymerization, where the alkene sort of unfolds, the double bond unfolds and creates a long carbon-carbon backbone. So the organic product from the esterification, we're going to maintain that alkene in the center of our molecule, and we're going to form two esters on either side, like so. In compound C, we're going to add steam and phosphoric acid, so we're going to have our carboxylic acids here, and one of these two carbons is going to be an alcohol. And finally, with the polymerization, we're going to draw the repeat unit of the addition polymer. Now we need our rounded brackets, N at the bottom, and our trailing bonds going in and out of the brackets on the left and the right.